Hi, everyone. Welcome back to 2.5. In 2.4, we introduced functions for the very first time, and now we're just going to look at some odds and ends properties of functions, so to speak. So the first two, very interconnected. Third one, similar to something we've done before. Last subsection, those other properties, kind of weird-looking things. One really nice, one not so nice. But let's get right into it. So increasing and decreasing. Your function is said to be increasing if your y values increase over some interval x1, x2. So if your ending y value is greater than your beginning y value, then your function is increasing on the interval x1, x2. Likewise, we say your function is decreasing if the y values go down on an interval x1 to x2. We say a function is constant if the y values remain the same. But one thing I want to stress here is that we are talking about intervals. Our answers for increasing, decreasing, and constant are intervals of x's. What we're trying to do is say on these x values, we're describing what is happening for y's. On this set of x values, the y values are decreasing. On this set of x values, the y values are increasing. We're not saying how much they increase. We're not saying how much they decrease. We're just saying from x equals 1 to x equals 2, we are increasing. You can kind of think about it like this too. Let's say you are driving in your car. At time 30 seconds, you are increasing your speed. So from time equals 30 seconds to time equals 40 seconds, you are increasing your speed. We didn't say how much your speed increased by. We just said on that 10-second interval of time, your speed went up. Now let's say you hit the brakes at time 90 seconds, and then at time 100 seconds, your speed is lower. So from the interval 90 to 100 seconds, your speed went down. Your speed decreased. Or you can also say your speed remained constant from time equals 2 minutes to time equals 3 minutes. Let's say if you're in like cruise control or something. So we're not talking about the y values. We're talking about the x values. Our answers are going to be in terms of x, but those x values are going to describe what the y's are doing. Okay, here we go. So let's say we have a graph like this. It extends forever in both directions. I just didn't put the arrows, but that's okay. So notice that things are a little different around these points. What I mean by that is let's follow the graph. Okay, on this graph, well, if we follow it, we are literally going up. So we are increasing up to the point -1, 2. So what this says is this: from x equals -infinity to x equals -1, the y values are increasing. So we say from -infinity to -1, again, these are x values, not y values. I don't care what the y values are. I only care on what interval of x's your function is increasing. So on this first interval, again, I don't care how high it increased. I don't care what it got up to. I just care that on this subset of x's, the y values went up. Okay, but at -1, something changes. We stop increasing and we start decreasing. We start going down. So we know we're increasing from -infinity to -1, but on the x values, -1 to 1, the function is decreasing. Again, no y values included. We're saying from x equals -1 to x equals 1, the function is decreasing. The y values are decreasing. Don't care what the y values are, only care to describe what they are doing. Last but not least, -1 to 1, we decrease, but at x equals 1, we change to increasing one more time. So notice this is an interval of x values. This is an interval of x values. This is an interval of x values. At no point do we use the y values. We are only describing what the y values are doing with some set of x's. That's really, really important. Now, in total, we like to write our answers as increasing all the increasing intervals together. So negative infinity to -1, union 1 to infinity. Likewise, decreasing, well, we only had one decreasing interval, so there we go. We like to write our answers as all the increasing ones, all the decreasing ones. However, it's easier for me if I just, show them to you one by one. But this is how we would formally write our answer. But on each individual interval, here's our answers. Again, sets of x's to describe what the y's are doing. Also, I want to stress that for increasing, decreasing, we're always going to use parentheses. It isn't quite clear. For example, at x equals 1, are we technically decreasing or are we increasing at x equals 1 specifically? Well, it's kind of a hard question to answer because the decreasing ends and the increasing starts. So instead of trying to say like, oh, well, it's decreasing on this part or it's increasing on this part, we're just always going to use parentheses for when it comes to increasing, decreasing. So this is not a coordinate point. It is an open interval. I know this is like the one time that we're really using similar notation for different things. Bear with me. All right, let's do another one. Here, let's start from the left of our graph and just follow along and see what happens. Okay, well, we start up here, and you'll notice that we are going down. So from negative infinity to x equals -1, our y values are decreasing. From negative infinity to x equals -1, the y values go down, so we are decreasing. But then at -1, we change. So from -1 to 0, we increase. From 0 to 1, we decrease. And last but not least, from 1 to infinity, we increase. So again, we do not care what the y values are. We only care what x values, for what set of x values do the y values increase and decrease. Notice we have this to say, oh, on this set of x's, the y values went down. On this set of x's, the y values went up. That's our goal here. Not including y values, only including x values each and every time. Okay, so in total, we like to write our answer all the decreasing and increasing intervals together. So we are increasing from -1 to 0, union 1 to infinity, and decreasing from negative infinity to -1 and 0, 1, with a union 0, 1. Okay. So that's increasing, decreasing. I think you guys get the idea. It's just gotta be really careful because again, you're gonna be so tempted to use the y values, but that's not what we're doing. We're using sets of x values. Just read left to right. From this x to this x, did we go up or down? From this x to this x, did we go up or down? That's what increasing, decreasing is. Now, extrema is a really fancy word for maximums and minimums. So technically, maximums isn't grammatically correct. It's technically maxima. However, I am very conditioned to say maximums and minimums instead of extrema or maxima and minima. Also, my name may or may not be Max. So in a lot of cases, I say maxes and mins. I don't even say maximums and minimums. So fancy phrasing. All it is this. Maximums occur when your function changes from increasing to decreasing. Think about what happens when your function changes. Let's say you're increasing, and then at some point you start to come back down. Well, that location at where it stopped increasing and started decreasing, that location at the top represents kind of a maximum value. Around that point, nothing is bigger than it. It might get bigger than it, down the road. That's where we get into different phraseology of what types of maximums. But where we change from increasing to decreasing. We call that a maximum. Likewise, we use minimums to say decreasing to increasing at the location that we change from decreasing to increasing. That is a minimum. So, big so here. The big difference from increasing, decreasing, and maxima and minima is that increasing, decreasing are intervals that describe what happens to the y's. But extrema, maximums, and minimums are specific locations in time or in space. Notice, we'll go back to this example. We're going to come back to this example in just a moment. But the increasing, decreasing were intervals, these long, smooth intervals of time where we were decreasing and then increasing and then decreasing and then increasing. But at the locations where it changes, those are maximums and minimums. So increasing, decreasing are intervals, extrema are points. So if your function does not change, well, nothing happens. I want to stress that maximums and minimums only occur when we change between increasing to decreasing or decreasing to increasing. So if your function doesn't change at some specific value, there is no maximum or minimum. What sometimes happens is you'll be increasing and then you kind of plateau, but then you increase again. In the event that you change from increasing to constant to increasing again, well, we didn't change specifically from increasing to decreasing. Maximums only occur when you change from increasing to decreasing, not increasing to constant, not decreasing to constant, only increasing to decreasing or decreasing to increasing. If it doesn't change in those only two scenarios, we don't call it anything. You might actually call something like this plateau a shelf, but that's not really important right now. How we phrase this is the extremum occurs at the x value, with the maximum or minimum being the value itself, being the y value itself. So let's go back to this example. We said we increased, and then at -1, we started decreasing. Well, we call x equals -1 a maximum. It changes from increasing to decreasing. Notice at the points right around it, there's nothing bigger than it. So this is a maximum. So there is a maximum at x equals -1 with a value of 2. Finally, we're using the y values. There's a maximum at x equals -1 with a value of 2. Okay, similarly, we are decreasing, and then at 1, at x equals 1, we change to increasing. Well, decreasing to increasing is the definition of a minimum. Okay, so there is a minimum at x equals 1 with a value of -2. And that's how we would formally write this. As you go along, it's totally fine to write maximum, with the coordinate point -1, 2. But as we're learning this for the first time formally, I want to make sure it's very clear what these things mean. Okay, let's go back to the second example again. We are decreasing from -infinity to -1, and then at -1, we change to increasing. Decreasing to increasing is a minimum. So there is a minimum at x equals -1 with a value of 1. Then we start increasing, and then at x equals 0, we decrease. So there is a maximum, right? Increasing to decreasing is a maximum. There is a maximum at x equals 0 with a value of 2. And last but not least, I don't think I need to go back, but there is a minimum at x equals 1 with a value of 1. So only maximums and minimums, they only occur when you change from increasing to decreasing or decreasing to increasing, respectively. Constant doesn't happen anywhere in that definition. staying constant, like increasing to increasing, also does not change there. So please don't use maximums and minimums for any other situation than those two changes. Okay, so a lot going on in those two, but let's talk about even and odd. And this is something we've actually kind of talked about before. We describe a function to be even if f of negative x equals f of x. Plugging in negative x wherever we see x, that sounds something really familiar. It sounds like symmetry. So even functions, if you replace negative x with x, are symmetric about the y-axis. So for example, f of x equals x squared is even, not necessarily because it has an even exponent, but if you plug in negative x wherever you see x, well, you would have negative x squared, and negative x squared is then positive x squared after simplification. So because f of x is the same as f of negative x, right? They both equal -2. They both equal x squared. In that case, this is an even function. Okay, so a function is odd if when you plug in negative x, you get the negative version of your function. Ooh, that's kind of weird. So odd functions are symmetric about the origin. And for example, x cubed is odd because when you plug in negative x, well, negative x cubed is negative x cubed. Okay, well, if we regroup this to say negative x cubed, well, x cubed is the original function. So this would be negative f of x. F of negative x equals negative f of x. This is symmetric about the origin, but we also call it odd. If you plug in negative x and you don't get either situation, that's totally fine. It just means your function is neither. That happens plenty of times. I also want to stress that we have symmetry about the y-axis and symmetry about the origin, but no symmetry over the x-axis. Well, let's say we have a graph that looks like this. Well, here's the x-axis, so this would be symmetric over the x-axis, but 2.4 is screaming. This doesn't pass the vertical line test. Maybe over here. Yeah, there we go. Sorry. I didn't expect to really be using my hands for this, but vertical line test. It crosses 2 points at once. Functions that are symmetric over the x-axis aren't functions to begin with. So we don't even need to talk about symmetry over the x-axis. Okay. Is this function even, odd, or neither? Let's see. Well, when we were looking for symmetry over the x-axis, y-axis, or origin, we had a specific method as to how we did it. Y-axis replace x with negative x. X-axis replace y with negative y. But doing even and odd, it's actually pretty nice. For all of these examples, go right for plugging in negative x, right? Notice f of negative x, f of negative x. Just go right for plugging in negative x for x. That's how we'll start doing even and odd. Okay, negative x cubed is negative x cubed. Negative 4 times negative x is positive 4x. Now, this is really similar to what we started with. Well, x cubed became negative x cubed, and negative 4x became positive 4x. Well, if we want to get the original coefficients, why don't we factor out a -1? Well, if we factor out a -1 from both, ooh, look at this. This x cubed minus 4x, x cubed minus 4x. This part inside the parentheses is exactly f of x. However, it's not perfectly f of x because we have a negative sign on the outside. Well, if f of negative x equals negative f of x, this is the definition of an odd function. So the conclusion here, f of negative x led us to negative f of x. That is the definition of an odd function right there. Okay, let's do another one. f of x equals x to the 10th plus x to the 6th plus 5. Wherever we see x, let's plug in negative x. Well, negative numbers raised to even powers are positive. Negative numbers raised to even powers are positive. Oh, well, actually, this is pretty quick. This is exactly like the other one. So f of negative x gave us exactly f of x. F of negative x equaled, after simplification, f of x. That's the definition of an even function. Okay. Well, you might be thinking, well, this example had all odd coefficients, all odd degrees. So it was odd. And this one had all even degrees. So this must be even. But what if we have both? Well, maybe you have an idea on that answer, but wait till you see the next example. All right, same thing. Let's go in for plugging in negative x. Negative x cubed is negative x cubed, so this will be negative 2x cubed. Negative x squared is then positive x squared. And notice that we can't treat this like the odd example. Here we have 2x cubed, and this is negative 2x cubed. So it would be nice if we pulled out a negative 1, but here we have positive x squared, and the same thing again. If we pull out a negative 1 to change negative 2 back to 2, well, then we would be changing x squared to negative x squared, and that's not what we want. That would be going backwards. There's nothing we can do to manipulate this to look exactly like the original function. In that case, if there's nothing we can do, it's neither. Okay. Well, so even exponents, it's even. Odd exponents, it's odd. Both exponents, both even and odd, it's neither. Well, how about this one? Here we have two even exponents in the numerator and two odd exponents in the denominator. It must be neither, right? Let's see what happens. Let's plug in negative x. So 3 times negative x to the 4th minus 5 times negative x squared. 4 times negative x to the 5th minus 2 times negative x cubed. Well, negative raised to even is positive. Negative raised to even is positive. Down here, negative raised to odd is negative. Negative raised to odd is negative. Well, negative is positive. Okay, well, the numerators are identical. 3x to the 4th minus 5x squared, exactly what we started with. But the denominators are off by a factor of negative 1. Positive 4x to the 5th, negative 4x to the 5th, minus 2x cubed, positive 2x cubed. So what if we factor out a negative 1 from the denominator? Well, we saw a couple times that if the denominator is negative, this technically means the whole thing is negative, right? If you were to redistribute this negative, you wouldn't distribute it to the numerator and the denominator. You would only distribute it to the to one or the other. Well, this, what is now inside the parentheses, is exactly the original function. Well, f of negative x equals negative f of x is the definition of an odd function. So, you can be easily fooled by degrees and exponents, so be very careful with that. It's just something that happens. That brings us to our last two properties of 2.5, things that are very different from the couple of things that we've talked about so far. Increasing, decreasing, extrema, and to an extent, even an odd are very graph heavy, but these next two, not quite. So average rate of change, you guessed it, literally the average rate of change. Your function changes over some time period. So if you were to graph this, I know it said not as graphic, but you're going to spend way more time doing this algebraically. Graphically, if you were to draw the slope of the line in between 2 points, that slope would be the average rate of change, right? You have some function over some very specific time interval. So from some very defined x to some very defined y. If you have those 2 points and you draw a line between them, the slope of that line is the average rate of change. So for some interval, x equals a to x equals b, the average rate of change is f of b, the value at b, minus f of a, the value at a, over b minus a. This looks a lot like y2 minus y1 over x2 minus x1. But now we have a very specific name. But also, when we talked about slope the first time, it was specifically for drawing lines. We're saying, what is the average rate at which your function changed over some time period, right? Your function can go up and down like crazy, but what's the average rate at which it changed? And that's what average rate of change gives us. Also, I might say AROC a couple times. It's a nice way of simplifying it. All right, so find the average rate of change from f of x equals 2 minus 3x squared from x equals 1 to x equals 3. In my opinion, it is probably in your best interest to solve for f of a and f of b first. A and b are always the beginning and endpoints of your interval. This is from 1 to 3, so a equals 1, b equals 3. There's nothing really surprising going on there. But instead of, trying to plug everything in to the average rate of change formula at once, do it in pieces, right? It ain't going to hurt you. Do f of a, where you solve the function with a plugged in, or more specifically 1 in this case. So 2 minus 3 times 1 squared. 1 squared is 1. 3 times 1 is 3. Negative 1. And take the time to do it for b as well. 3 squared is 9. 3 times 9 is 27. 2 minus 27 is negative 25. So take the time to do that. Don't try and plug it all into the AROC formula right away. Okay, well, average rate of change, f of b minus f of a over b minus a. Well, we just found f of b, and we just found f of a, and b is 3, and a is 1. So that's actually pretty nice. We already have everything. Negative 25 minus negative 1, that's plus negative 12. So the average rate at which our function changes from 1 to 3 is negative 12. If you were to draw a line from 1, negative 1 to 3, negative 25, its slope would be negative 12. Let's do that again. X cubed plus 1 from x equals negative 2 to x equals 4. Well, we start from a, end at b. So a is negative 2, b is 4. Let's find f of a, f of negative 2, by plugging in negative 2 to the function. Negative 2 cubed is negative 8. Negative 8 plus 1 is negative 7. F of b says plug in b, plug in the final endpoint. Well, 4 cubed is 64. 64 plus 1 is 65. F of b minus f of a over b minus a. Well, we got f of b right here. We got f of a right here. And we have a and b right here as well. Bunch of minus minus plus 72 divided by 6 is 12. Average rate of change. Not anything super crazy. But that brings us to our very last property for 2.5, and that is the difference quotient. So its meaning is kind of crazy because we haven't spent a whole lot of time talking about this, but difference quotient is a method to find the formula for the slope of the tangent line at any point on the graph. So imagine you have some curve and you want to find a tangent line to any point on that curve. So let's say tangent lines in general, let's say you have a graph that goes like this and it comes down. But what if instead of coming down, we wanted to draw a line at the point where it is still going up? We draw a line tangent to the graph. Kind of difficult to explain. Actually, you know what? I'm going to take a second and show you what this looks like. What would a presentation be without a single thing on the whiteboard? So let's say you had some graph that looks like this. If you wanted to draw a tangent line, so a tangent line would be a line that kind of like touches at one specific x value and goes in the direction that it was heading. So at this point, tangent line runs like this, but down here, tangent line would run like this. So imagine like you're throwing a baseball, and when you throw a baseball, when you let go, the ball travels in the position that you were letting go, or in the direction of where you would have let go. If you let go of the ball too late, you throw it to the ground. If you let go of the ball too early, it goes up in the air. But if you try and throw it straight, you have to throw it at a very specific time. So that's what tangent lines are. I realized in a digital setting, not as easy to describe, but that's what tangent lines are. So what the difference quotient is doing is getting us a formula for the slope of that tangent line at any point on the graph. So difference quotient is given by this. Oh, didn't I say this thing was going to come back from 2.4? Sure is. Difference quotient needs f of x plus h. All this is the function with x plus h plugged in, the original function, and h is going to be just some constant that we don't know. So let's find the difference quotient for 2x squared minus 3x plus 5. We need f of x, we need f of x plus h, and we need h. Well, h is just h, and f of x is sitting right there for us. So all we need is f of x plus h. This says wherever we see x, plug in x plus h. All right, here we're going to have to FOIL. Here we're going to have to distribute. Here we're going to have to distribute 2. So I know I skipped through a lot of that, but we've been doing this stuff since like chapter P. It's just a matter of, this is the new step of plugging in x plus h wherever we see x. So this is all of f of x plus h. And we want to plug this into f of x plus h. And we want to plug this in for f of x. So taking f of x plus h, taking f of x, and plugging them both in, we get this ugly monstrosity. So here, let's distribute our negative sign, right? Plugging in f of x, use parentheses. Let's distribute the negative sign. And now, you think it doesn't get any better, but it actually does. 2x squared minus 2x squared. Oh, that goes away. Minus 3x and plus 3x. Oh, that goes away too. And positive 5 and negative 5. Well, out of 9 terms that we have here, 6 of them just canceled out. 2x squared minus 3x plus 5. Well, minus 2x squared plus 3x minus 5 canceled out all of those terms. And we're left with these 3. Now, we're almost there, but notice this. Every term in the numerator has an h. So let's factor out h. And if we have h times something divided by h, we can cancel those h's out. And we're left with just 4x plus 2h minus 3. Now, we are not even close to Calculus 1 just yet. That is coming in, 2 courses if I ever make those videos. But this is one step away from being the first derivative. So that's actually a very interesting piece of information that we get. So that's the difference quotient. Like I said, it's a Calculus 1 thing, but notice that there was nothing here that we weren't capable of doing already. So that's difference quotient. Weird, very strenuous algebraic activity. This was kind of a decent amount of work for not a very exciting final answer. But we can get them to look really, really ugly. Let's do one more. That's just a polynomial, but we'll call it after that. So difference quotient, we need f of x. We need f of x plus h. We need h. H is just h. F of x is just itself, but we need f of x plus h. Wherever we see x, plug in x plus h. We're going to FOIL x plus h squared. We're going to distribute this outer negative sign. And now all of this information, f of x plus h and f of x, are going to go into the difference quotient. Alrighty, how beautiful. Let's distribute a negative sign to each term in here. And we see negative x squared cancels out with positive x squared. Positive x cancels out with negative x. And negative 3 cancels out with positive 3. All of these terms in the numerator have an h. Let's factor out h. H then cancels out. If you did this right, you should have something like this that happens, and you're left with negative 2x minus h plus 1. And that's the end of 2.5. So some very interesting properties, right? Increasing, decreasing, and maximums and minimums, kind of along with difference quotient, is something you will study very in depth in Calc 1. But even odd, it's kind of just an extension of symmetry we talked about in 2.2. So that's the end of 2.5. We're going to change gears a little bit in 2.6 and talk more about graphs of functions, very specific graphs of functions, but not really a ton of new information there, just looking at some of the weird types of functions that we actually have. So with that said, I will see you in 2.6. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.